repeat the title. So today we have Luca Delacretaz from University of Chicago talking about hydrodynamic fluctuations. Please, Luca.
Okay. Yeah, thanks a lot for the introduction and the opportunity to speak. And thanks to you and the other organizers for keeping this this conference alive against all odds. I really enjoyed watching the last few talks remotely. Okay, so this talk will be about hydrodynamic fluctuations. There were already a few talks on or related to hydrodynamics in this conference. In particular, there was a really nice talk by Natalia on an effective field theory formalism that can capture these hydrodynamic fluctuations. So this talk will be complementary to her talk in the sense that I'll focus on the application of this formalism, namely on hydrodynamic fluctuations themselves. And since I'll focus on the application, I'll try to make it as non-technical as possible. And also you should feel free to interrupt me with questions at any time. So I probably don't have to sell the merits and the importance of hydrodynamics to this crowd, but let me just say a few words. Hydrodynamics is inevitable. It's there whether you like it or not in thermalizing system. And it's very universal, doesn't depend on the microscopics. And in a sense, directly maps a set of symmetry assumptions on the system you're looking at to observables like correlation functions. So it's okay. So it's very universal. It's highly relevant for experiments. We better understand it. We often think of hydrodynamics as a set of classical equations that we can kind of solve to get correlation functions. But the hydrodynamic fields, the collective excitations that make these hydrodynamic fields, can fluctuate themselves. And the point of this talk will be to explore the consequence of these hydrodynamic fluctuations. So let's get started. So as I said, any thermalizing system, whether it's quantum or classical, will be described by some form of hydrodynamics at late times. And the appropriate hydrodynamic description only depends on the symmetries, the global symmetries of the system. So just to name a few examples that you can have, for example, if you have energy or charge conservation, what you typically land on is a hydrodynamic theory of diffusion. Whereas if you have momentum conservation, you can get the Navier-Stokes equation, and so on. And really what's important here is that the hydrodynamic description only depends on symmetries. Systems with very different microscopics can have very similar hydrodynamic descriptions, which is why hydrodynamics is useful in so many fields, like condensed matter physics, but also high energy, soft matter, or statistical physics, and so on. So the first question that comes to mind is, how is such a universality possible? And the kind of simple explanation for this is that at finite temperature in generic systems, most excitations relax with some time scale that I'll call the thermalization time. So that if you wait for times later than this thermalization time, your system becomes very simple. And it's left with the quantities that can't relax because they're conserved. Conserved charges won't change. And conserved densities, their relaxation rate will be proportional to some power of their wave vector. So as long as we focus on the long distance physics, work with small enough wave vectors, these densities will be parametrically longer lived than generic excitations. And then hydrodynamics is basically the late time description of these coarse-grained quantities. So here I introduced an important quantity, the thermalization time, which you can think of as the onset time of hydrodynamic behavior. Or another way to think about it is as the UV cutoff of hydrodynamics. And just to give you a few examples, so in a system whose microscopics is weakly coupled, this thermalization time will be parametrically slow. It's going to be parametrically large in 1 over the coupling, because you have to wait a long time for the weakly coupled particles to collide and thermalize. On the other hand, in strongly correlated systems at high temperatures, we expect the thermalization time to be of order this famous Planckian time scale. All right, so let's see how it works in the simplest possible case where I have a single conserved charge, which could be charge or energy conservation. So it's going to be subject to a continuity relation like this because it's conserved. Now this equation also involves the current, which itself is not a slow density. However, at late times, the only stuff left in the game is these slow densities. So the current is going to have, we can expand the current in terms of these slow densities, and we'll do so in a gradient expansion. Okay, this is called a considerative relation. And the first term I can write down is this single gradient term here, which involves a coefficient that I don't know, that I'll call the diffusion constant. So then plugging this back into this equation, I get an equation for charge itself that I can solve. I can linearize around some charge density, and this will lead to this diffusive Green's function for the charge density, which has a single pole, a diffusive pole here that I plotted in the complex frequency plane. And this excitation is carried by this charge density. So here it's important to note that there are two expansions going on. There's a gradient expansion. As I said, there's going to be higher gradient terms here. And that expansion is always controlled, at least in principle, because as long as I focus on small enough wave vectors, these terms will be suppressed. But there's another expansion, which is an expansion in fluctuations of the fields. And this expansion is more subtle. It's only going to be controlled when interactions are irrelevant. And we'll see exactly when that happens. So here in this simple theory of a single conserved quantity, we got this simple diffusive mode, but as probably all of you know, more things can happen. A simple example is in regular fluid dynamics, where you have conserved energy and momentum. Here I worked out the relativistic case, but the non-relativistic case is similar. So in this case, the conservation laws look like this: conservation of the stress tensor. And again, we have to relate the currents back to the densities, the flow densities, or their associated potentials. And this is done through a considered relation like this, okay, which involves the pressure, energy, bulk viscosity, shear viscosity. And so again, we can get correlation functions for the stress tensor here by linearizing around equilibrium. And what we land with is a retarded Green's function for the stress tensor that looks like this. It has, again, a diffusive pole with a diffusion constant related to the shear viscosity, and a sound pole with some sound attenuation. So these are the two kinds of modes, these sound modes and diffusive modes, that I'll be focusing on. They're all over the place in hydrodynamic theories. So basically, a diffusive mode looks like this. It has, if you start with some kind of lump of charge, it's going to spread out in time diffusively, keeping the area of this under this curve fixed. Whereas a sound mode or a ballistic mode propagates with some velocity and then spreads. So if I follow this pulse, I'm going to see it spread kind of, diffusively in time. And the reason I want to focus and separate these two cases is that their fluctuations are going to be quite different. So we'll see how in a bit. And just to illustrate, that these types of modes are all over the place, to give a few examples without going too much into details. So in a regular fluid, we saw that there was a sound mode that will look like this. It's carried by the energy density and the momentum, longitudinal momentum. And we found a diffusive mode in the shear momentum channel. But if the fluid is charged, there's going to be an extra diffusive mode carried by charge. Now, you might be interested in the hydrodynamics of a system that has these symmetries, but where the U1 charge conservation symmetry is spontaneously broken, so that you have a superfluid. And in this case, the extra degree of freedom, the superfluid phase, kind of hybridizes this diffusive mode and gives you an extra sound mode, the second sound of superfluids. And some of you have been studying these systems with translation symmetry breaking instead, like charge density waves or Wigner crystals. In this case, you also have extra goldstones that can hybridize these modes. So we have, there's a lot of examples of these types of modes in a lot of different systems that are carried by densities or goldstones. There are some other types of modes that I won't be talking too much about. You can have, especially in anisotropic systems, you can have modes that look sound-like in some direction, but diffusive in another direction. This happens in stripes, for example, but also Alfvén waves in MHT. You can also have modes whose real part of the pole is higher order in K. This happens for so-called type 2 goldstones, like spin waves in a ferromagnet. And you can definitely cook up more exotic cases. But just for simplicity, I'll be focusing on these two cases. We'll see that they're already rich enough in terms of hydrodynamic fluctuations. So the first important question I want to address is when are fluctuations big? When are hydrodynamic fluctuations big in these cases? So let's look at the diffusive case first. So this is the hydrodynamic equation of motion that led to this diffusive mode. And now we want to see the effect of nonlinearities. So where do these nonlinearities come from? One place that they can come from is from the fact that the diffusion constant can depend on thermodynamic parameters like the charge density. There's no symmetry reason for it not to. So in general, it will. And so what I can do is Taylor expand this diffusion constant around my background charge density, so that the zeroth order term will just be this diffusive equation, but I'll have a a correction that's nonlinear in charge fluctuations. And that involves the derivative of the diffusion constant with respect to charge density. So now we'd like to figure out how important this term is. So to know this, we need to know how to scale charge fluctuations. And there's an easy way to figure that out. You just have to remember what a diffusive two-point function looks like in space and time. So it looks like a Gaussian that spreads in time. It's basically what I drew here in red. And there's an overall power of time that you can find by remembering that if you integrate this correlation function over space, this will give you the total charge, so it better be constant. And that's indeed what integrating this Gaussian gives. So from this, we learn how charge scales with time or with frequency. It scales like frequency to the d over 4, which means that it scales with wave vector, or k, to the d over 2. Okay, so if we go back to this equation, we have our first two leading order terms that scale like k squared, omega and k squared. And this nonlinear term, compared to this term, just has an extra power of the charge density. So it has an extra power of k to the d over 2. So we see that it's always going to be suppressed at small wave vector, since d is going to be positive. So in this sense, interactions will always be irrelevant for diffusive systems. What about ballistic modes? So we can do a similar analysis for a ballistic, a kind of ballistic mode. This mode is going to have some kind of velocity. It's also going to have a damping, but the velocity is now more relevant. It has less gradients. So let's see what expanding this velocity leads to. So it's going to lead to these two terms, this nonlinear term that involves a single gradient. And to study how relevant it is, what we can do is go in the reference frame of the pulse. Okay, so just follow the pulse, so that these two first terms just become a single time derivative in this reference frame, and I have just kind of diffusive spreading in this reference frame. And in this frame, charge fluctuations again will scale like k to the d over 2. So that now, if we compare these terms, we again have k squared from the linearized hydrodynamics part. And this nonlinear term has a single gradient times the charge fluctuation. So it's going to go like k to the 1 plus d over 2. So here we see that the critical dimension is 2. And in dimensions smaller than 2, interactions will be relevant and charge fluctuations will be large. Something is going to happen there. So to summarize, hydrodynamic fluctuations are weak for diffusive modes all the time, and for ballistic modes in spatial dimensions larger than 2. And they're strong for ballistic modes in spatial dimensions smaller than 2. So maybe this is a good time to pause to see if there are any questions and if you guys are still alive.
I forgot to say that if anybody wants to ask a question, just please unmute themselves and just ask. It looks like nobody's asking, but we are alive at least.
Okay, at least you are. We don't know about the others.
Come on, there's 40 people.
Okay. Hopefully it's not bots. Okay.
Yeah, probably. Can I ask a question at this point?
Yes.
Yeah, go ahead. As I said, just go ahead when you have a question.
Yeah. So this is just dimension on how things scale.
Yeah.
When we do ADS-CFT, usually we ignore these fluctuations, right?
Yes,
yes.
It
seems so. Usually the logic is that there are many more fundamental modes than there are of these hydrodynamic modes, right?
Exactly.
Yeah.
Yes. Yeah, that's a very good point. And especially since this is the hollow matter series of talks, I should mention that these fluctuations are suppressed in the number of degrees of freedom. So they do occur in holography, but it's 1 over n or 1 over n squared effects, and they're a bit harder to see in holographic systems.
Okay, thank you.
Yeah. Any other question? Okay.
But in
sorry.
In that counting, gravity itself is a 1 over n effect. So I'm not quite sure what the meaning of the last comment was.
Sorry,
gravitational
fluctuations
are 1 over n or 1 over n squared effect, and yet they can be significant in many contexts.
Right. So I was saying that effect of hydrodynamic fluctuations compared to the tree level hydrodynamics, like the fact that you have a diffusive mode or a sound mode, the relative suppression of these two things is 1/n.
Okay.
So you have the first thing, if you do holography, you will see, you know, these modes, diffusion and all these things, but fluctuation corrections will be suppressed. So even if fluctuations were strong, you would have this 1/n suppression relative to the tree level hydrodynamics.
Okay.
All right. So in the rest of the talk, I'll try to illustrate both of these situations when what happens when we have weak and strong fluctuations. And I'll do this by taking an example in each case. And I'll try to take the simplest possible example. So for weak fluctuations, I'll look at diffusive mode. In fact, I'll look at a single diffusive mode in any dimension. But a lot of the consequences will apply to more general situations where fluctuations are weak, including ballistic modes in more than 2 dimensions. And for strong fluctuations, we'll have to go to 1 dimension and look at a ballistic mode in 1 dimension. So here I'm again going to look at a case where I have a single ballistic mode in 1 dimension. And this will allow me to talk about this recent paper with Paulo, where we found that the edge of quantum Hall systems have very large hydrodynamic fluctuations and a breakdown of this diffusive spreading. All right, so but before getting into that, let's get warmed up on these with these weak fluctuations. So okay, so we found that diffusive fluctuations scale like k to the d/2, and they're always irrelevant. So what this means is that we have a controlled perturbative expansion in these fields, in these fluctuations. So it's really a very similar situation to regular effective field theory, where you have a semi-classical theory with degrees of freedom that are approximately free in the deep IR, and you look at the effect of the leading irrelevant interactions. And so this study is called the theory of hydrodynamic fluctuations. It was pioneered in these papers, but has a long history. And I won't go into too much detail into how they did it back then, but just in a nutshell, basically what they did is to add a noise term to these considered relations, which show the deviation, so which parameterize the deviation of the current compared to its equilibrium hydrodynamic value in terms of the charge density. And the fluctuations of the current will be fixed to the dissipative terms, the diffusion constant, by the fluctuation dissipation theorem. So how much the current fluctuates away from this equilibrium value is proportional to how much it will respond to an electric field if you turn on an electric field. And what these early papers did was basically engineer an effective field theory that reproduces these equations of motion. So here already an interesting thing we see is that there's a kind of doubling of degrees of freedom. Every hydrodynamic field will have an associated noise term. So much more recently, there's been a lot of work on putting these effective field theories on a more firm footing, in particular starting from symmetries, just deriving them from symmetries. And one thing that I really like about this more recent work is that it explains a little more clearly where this doubling of fields is coming from. Namely, so the explanation is the following. We're in a thermal state, so we need to time evolve a density matrix, which has two, it's a density matrix, a thermal density matrix, so it has 2 legs. And so the natural way to time evolve it is on a Schwinger-Keldysh contour. And so so our path interval will be formulated on this Schwinger-Keldysh contour, and this will naturally lead to doubling of degrees of freedom. And under RG, these degrees of freedom will mix. This is nicely explained in this paper. And in the IR, we'll be left with some effective field theory where both of these degrees of freedom are interacting. So the mapping between this formulation and the older one is roughly as follows. The average of these fields is related to the hydrodynamic densities, whereas their difference is related to these noise fields. The mapping between these two formulations is explained a little more precisely in this paper. But for the purposes of this talk, I'm going to use a slightly simplified treatment of hydrodynamic fluctuations just to kind of put some technical complications under the rug and focus on conceptual, on kind of qualitative features. And the idea is basically the following. So we know from these effective field theories that the hydrodynamic fields are semi-classical. So if we want to compute, which means that they'll approximately Gaussian factorize. So basically, if we want to compute 2-point functions of the current, for example, we can just use its expansion in terms of charge densities, and then just Wick contract, Gaussian factorize these correlation functions. So let's try to do that. Let's compute the current 2-point function. We'll have Feynman diagrams that look like this. The linear term will give us this constant piece, which is just the Einstein relation for a diffusive system. The DC conductivity is a constant. But then we'll have this one loop correction to this leading behavior, which goes like, you can compute the loop using the free, just diffusive propagators here. And what you'll find is a correction that goes like frequency to the d/2. So notice that this correction is going to be small at small frequencies. It's a small correction. This is a manifestation of the fact that interactions are irrelevant. But it's interesting because it's non-analytic. And in particular, in one dimension, it's bigger than the leading higher derivative correction, which will be analytic. So even though it's a small correction, it can still be seen. It can still affect, it can still be seen. For example, in numerics, here these people did exact diagonalization in a quantum spin chain and saw this kind of square root behavior. So this is an example of what's called a hydrodynamic long time tail. They were originally discovered numerically in classical numerics. And this paper is kind of what started this whole field of hydrodynamic fluctuations. As I mentioned before, you can also see, you can even see them in holography, where you have to do some work. You need to compute a graviton loop in the bulk. Because these tails, I didn't write it here, but there's a suppression by basically the local degrees of freedom. So they're going to be 1/n suppressed in large n theories. And there's been some recent interest in the context of quark gluon plasma for these long time tails as well. Okay, so one thing we can also look at is the effect of hydrodynamic fluctuations at finite wave vector, and we'll see some interesting things happen. So we can do a similar calculation, but keeping the wave vector finite. And what you find, so you can kind of resum these one loop corrections to charge diffusion, and you get a self energy, a kind of universal correction to diffusive behavior. And this self energy looks like this, so it's not analytic. Okay, it's coming from a one loop correction. If you look at the total power of k, you'll find that it's some positive power of k, this expression. So it's always a subleading correction to diffusion. Okay, again, a manifestation that interactions are irrelevant. But it has this interesting non-analyticity, which is not at the diffusive pole, but rather halfway to the diffusive pole. That's where the branch point starts. So this might remind you of the analytic structure of propagators in quantum field theory. If you have a free massive particle, it just has a single pole at the mass at p squared equals m squared. But if the particle is weakly interacting, it's going to have a branch cut with a branch point that starts at the threshold for production of several particles, of 2 particles here. And so a similar argument can be used to found the location of this branch point without doing any hard loop calculation. And the idea is basically to just take one of these diffusion loops, cut it, and put the internal legs on shell. So basically, I'm going to impose that both of these legs sit on the diffusive pole. And then you look for the smallest frequency at a fixed k that can satisfy these 2 equations, and that's how you can land on the location of the branch point. So it's a bit surprising that the location of the branch point is even closer to the origin than the single pole. It looks like it might swamp the IR behavior and basically hide regular diffusive behavior. But the reason this doesn't happen and that diffusion survives is that the discontinuity across the branch cut is suppressed by gradients. So it's just a small correction to the Green's function. If you're not satisfied with this argument for the location of the branch point, there's an even simpler argument in real time. And actually looking at correlators in real time will lead to a surprise. So I want to go over this argument. So let's again try to go through the same thing, but for a correlation function at finite wave vector as a function of time. So here this O is some operator that's allowed to overlap with various powers of the charge density. And so the leading correlation function in the diffusive system will be controlled by a single diffusion, and the correlation function for diffusion in time and wave vector looks like this. So things decay exponentially, but with a very slow decay rate with the diffusion time. But here the higher loop corrections will involve two diffusive propagators. And really it's going to involve a loop over an integral over the loop momentum. But basically the part that will dominate is when you give half your momentum to each diffusion. And so what this is going to look like, each diffusion is going to have half the momentum. So there's going to be a k over 2 squared. And then I'm squaring the whole thing. And so that's how you get this factor of 1 over 2. Okay. And then this prefactor is there again because interactions are irrelevant. So this term is suppressed at small wave vector. So the leading behavior will be this first term, at least at times not too late, so that the exponent doesn't matter. Okay, so if we're at times later than the thermalization time, but before the diffusion time of the mode at that wave vector, we'll have this behavior. But if we wait a bit longer, these exponents are going to start to matter, and this 2 diffusion decay channel is actually slower because of this 1/2 than the single diffusion channel. So at late enough times, it's going to be able to overcome the suppression by powers of k. And the 2 diffusion channel is going to control the correlator at late times. So this should kind of raise a red flag. I just told you that interactions are irrelevant, but somehow these irrelevant interactions are controlling the leading behavior of the correlation function at late times. And I should say, since we talked about holography, that in a large n system, there's an extra factor of log n, so you have to wait a bit longer, but this will also happen if you wait for times larger than diffusion time times log n. Okay, so this is an example of dangerous irrelevance. We have an irrelevant interaction that actually, if you that kind of comes back to haunt you. And this doesn't stop here. At some point, the higher order terms are going to be important. We can look at the contribution of an n diffusion term. So it's going to be, because again, interactions are irrelevant, it's going to be even more suppressed. We'll have a larger prefactor, k to the d times n. But for the same kind of kinematic reasons, the exponent is going to be slower. So at times later than the diffusion time, we can kind of figure out there's going to be a competition between the suppression due to irrelevance and the reduced decay rate. And the channel that dominates, the number of diffusion in the channel that dominates will depend on time. And you can just find it by finding the biggest contribution, and it grows with the square root of time. So if you plug this back in here, you'll find that the correlation function at these late times, instead of decaying exponentially, decays with this stretched exponential behavior, like e to the minus square root of t. So on a plot, this is what it would look like. So here I'm plotting the correlation function at finite wave vector in a diffusive system as a function of time. At times earlier than the thermalization time, hydrodynamics doesn't tell me anything. It's going to be sensitive to the microscopics. After the thermalization time, the dominant decay channel is just going to be regular diffusion, and things are going to decay in this way until at times roughly the order of the diffusion time of this mode, where I have this cascade of this diffusion cascade. I decay into more and more diffusons, and it leads to this slower stretched exponential behavior. So in the thermodynamic limit, this would just go on forever, the stretched exponential. But in a finite system, if I'm in a finite system, there's going to be a smallest wave vector that these diffusons in the loop can have. And so that's going to kind of limit this, the cascading is going to stop at some point. And the decay will again be exponential at late times. And the time at which this happens is called the Thouless time. So it's a time that scales with the power of the system size. So then this decay will go on until the correlation function is exponentially small. And then in a quantum system, that's when you would expect to see onset of random matrix theory, but that's beyond hydrodynamics. Okay, so we have this kind of rich behavior of correlation functions, even in the simplest diffusive systems. That's the main thing I wanted to say about weak fluctuations, and I hope this gets you excited for what's going to happen when fluctuations are strong. But maybe I'll pause here for questions before going on.
Okay, can I ask a question?
Mm-hmm.
So this discussion now was based on analyzing diffusive behavior.
Mm-hmm.
But we know that in the relativistic context, diffusion isn't really consistent because you get modes which eventually propagate faster than the speed of light, the frontal velocity is infinite and so on. Does this have any influence here on I mean, there must be somewhere K value where this has to break down in the relativistic context.
So I don't think so. The kind of superluminalities that you talk about of diffusion happen at times earlier than what I would call the thermalization time. So diffusion is naively superluminal at early times, but I'm not going to trust hydrodynamics there anyways. And in fact, we know that it shouldn't be trusted just because of one good reason not to trust is because of it should be relativistic. But I don't think it will affect. I don't think this constraint of subluminality is very constraining for the hydrodynamic behavior.
Okay, thanks.
Maybe I can make one more comment, Pavel Kovtun here. This causality can be restored by high-dimensional operators in your language, irrelevant operators. Yeah.
Mm-hmm. Exactly, yeah. Which also tells you that it has to do with the UV. Yeah. Thanks for that comment. Any other questions or comments? Okay. All right, so let me move on to strong fluctuations. So here the system, let me tell you about the system we're going to consider. So now I'm actually going to talk about a physical system. So the systems we're interested in here are quantum Hall systems, which are gapped. But as you probably know, the edge of quantum Hall system supports gapless excitations. They're often thought in terms of chiral channels or CFTs and so on. As theorists, we like to think of these of the quantum Hall problem at zero temperature. But on the other hand, it's been known for quite some time since this paper, I think, that thermalization on the edge is crucial to explain the experimental data. Because if there wasn't thermalization, you would see experimentally this huge number of edge modes. For some fillings, there's a large number of chiral liquid channels that are predicted on the edge, and they're just not seen. Experimentally, what you see, the modes you can see propagating on the edge are the charge mode and sometimes the heat mode. So they're related to conserved quantities. They're hydrodynamic modes. Whereas the other modes are kind of lifted, relaxed by thermalization. So we know thermalization happens, at least in a number of quantum Hall systems. And the natural question I want to ask next is, what is the hydrodynamic description of the edge? And so here I want to stress that I will not assume that momentum is conserved. So this discussion will be robust against disorder. And I'm basically only going to assume charge conservation, which is anomalous. And in a nutshell, let me give you our kind of results in a nutshell before going into details. So the collective charge excitation, we'll see that because of the chiral anomaly, it's ballistic instead of diffusing. So it has this kind of, at the linearized level, it has this kind of biased diffusion behavior that was pointed out in this paper. But as you now know, we should be careful with ballistic modes in one dimension. And in fact, we'll see that hydrodynamic interactions are relevant in this system, and they lead to a breakdown of this diffusive spreading of this chiral front, and instead drive the system to a new dissipative universality class, which is the so-called KPZ universality class, and which in particular has a dynamic critical exponent of z equals 3/2 instead of z equals 2 in diffusion. So there's still a chiral mode, okay? That's still true. In fact, it's kind of protected by the anomaly in some sense, but its broadening is anomalous, and it broadens with wave vector to the 3/2. Another consequence of these large hydrodynamic fluctuations is that they lead to singular low frequency transport on the edge. The optical connectivity on the edge, instead of satisfying the Einstein relation, instead of going to a constant at small frequency, is singular and diverges like 1 over frequency to the 1/3. So here I want to stress that this is a small a singularity at low frequencies, which is pretty unusual. Usually, precisely because of hydrodynamics, connectivities and response functions are analytic at low frequencies, at frequencies much smaller than the temperature, for example, because hydrodynamic correlation functions are usually analytic, and instead the kind of non-trivial physics is in the temperature dependence, for example, of transport parameters. So the only way you can have these kind of singular optical connectivities at low frequencies is when hydrodynamics itself breaks down and hydrodynamic fluctuations are large. Okay, so we'll also see that heat diffusion similarly breaks down, but I'll focus on charge first. And there's some generalizations to higher dimension that I might talk about in a bit. So there's kind of 3 cool aspects that appear in this problem that I want to mention. The first is that there's an interesting hydrodynamic theory that describes a condensed matter system without momentum being the long-lived quantity. So it's not, this hydrodynamic description is not, it is robust against disorder. Okay, I'm not, in fact, disorder is on our side. It's getting rid of the things of momentum, which we're not assuming is conserved. The only conserved thing will be charge. The other cool thing is that there's an anomaly. There's the 2D chiral anomaly. And it's been appreciated for some time, the effects of anomalies in hydrodynamics. They lead to a number of phenomena. And often these phenomena are pretty subtle, but here it leads to a very dramatic phenomena, which is that it's going to cause, and this is the last point, it's going to cause large hydrodynamic fluctuations. Okay, so let's see the problem we have. So it's really the same as before. We have a single charge with a continuity relation, and the only difference is that there's now an anomaly, the 2D, the 1 + 1D chiral anomaly, which in this notation looks like this. So basically, what it's telling us is that if I turn on an electric field, then there's an inflow of charge from the bulk of my quantum Hall system to the boundary, and the anomaly coefficient. So here I'm dropping factors of 2π and so on. But the anomaly coefficient is given by the filling fraction of the quantum Hall system. Okay, so it's been understood how to incorporate the effect of anomalies in hydrodynamics since this paper. Basically, anomalies fix terms in the considered relations. And in this original paper, they were looking at the 3 + 1D chiral anomaly, where the anomaly fixes a 1 derivative term in the considered relation. But the 1 + 1D chiral anomaly fixes a 0 derivative term in the considered relation, namely this first one here. And then I'll have the usual diffusive term. Here I just wrote it in terms of the chemical potential instead of the charge. Okay, so this leads to an equation of motion for charge that, instead of being just diffusive, has this ballistic part with a speed of sound that's related to the anomaly. But the speed of sound itself is not universal. It's not some protected number. It also involves the charge susceptibility. Okay, so now we could first linearize these equations like before to get a kind of tree level, Green's function, and it's going to look like this. It looks diffusive, except it has this kind of biased diffusion behavior. There's a ballistic part with some diffusive spreading. So if I start with a lump of charge on my edge, it's going to propagate. It's going to be right moving, for example, depending on the sign of filling, and spread diffusively. Okay, but of course, as you know now, we should be careful with nonlinearities, and in particular, the velocity, since it's not universal, it can depend on thermodynamic quantities like the charge density through the charge susceptibility. Okay, so we'll have nonlinear terms like this, and as we saw before, these nonlinear terms, since we know how to scale charge, are relevant. They're more important than the leading dissipative term. And so they will lead to a breakdown of diffusion. So this is telling us that something interesting will happen, but it also tells us that we lost perturbative control. We no longer have a kind of a semi-classical effective field theory. So what can we do? how can we regain control? So one thing we could do is do dimensional regularization. As we saw, things become less relevant in higher dimensions, and we know that the critical dimension is 2. So we could work in 2 dimensions and then kind of do epsilon expansion to study perturbatively what's happening. And this can be done. In fact, the theory, this kind of generalization of this theory to 2 dimensions is interesting in its own rights, because it describes these so-called chiral surface metals, which are layered quantum Hall systems. So we look at this in the paper, in fact. But can we be more ambitious and hope for an exact solution in 1 dimension? So if you come from the quantum critical community, you'd probably think this is hopeless. We have a relevant interaction. There's no small parameter in the game. How will we be able to say anything exactly? But it turns out that the world of dissipative physics in 1 dimension is a bit magical. There's some kind of non-renormalization theorems. And some things can be said exactly. And the first example of such a treatment, I think, was in this paper, where they looked at the Burger's equation. Maybe a slightly more famous example is the KPZ equation, which actually is the exact same equation as the Burger's equation. And in a slightly more recent paper, these people looked at the Navier-Stokes equation in 1 dimension and were able to say some exact things. So we will be lucky. We will be able to make some exact statements. In fact, this equation will exactly map to the KPZ equation. So if you know the KPZ equation, I'll quickly explain how the map works. Otherwise, it's not too important. So this is our anomalous diffusion equation. We have this ballistic part, diffusive spreading around the ballistic part, and this is the nonlinear term that's causing us troubles. So the first thing we can do is just follow our pulse. Okay, work in the reference frame of the pulse so that we can get rid of this ballistic part, and then we just have a diffusive spreading and this nonlinearity. And then this equation directly maps to the KPZ equation, where charge maps to the gradient of the height in the KPZ equation. KPZ equation is about surface growth, so the important variable is the height, or the slope, actually. All right, so basically we learned that the edge of quantum Hall systems is in the Burger's KPZ universality class. And a lot is known about this universality class. In particular, the dynamic critical exponent is fixed. So let's see what consequence this has for hydrodynamics on the edge. So the first consequence is that the collective excitation will have this dispersion relation. So it's still going to be ballistic, but it's going to have this anomalous broadening with this critical exponent. And the analog of a diffusion constant is actually also fixed in terms of thermodynamic parameters. And I really like this formula because it shows the 3 ingredients that were necessary for the breakdown of diffusion in this system. So the first is finite temperature. We're talking about fluctuating hydrodynamics. We need temperature in the game. The second is the anomaly. Remember that if the anomaly is 0, I just have regular diffusion, and that, as we saw before, is weakly interacting. And finally, we needed these hydrodynamic nonlinearities, which came from the fact that the speed of sound depended on charge. This is the derivative of the speed of sound with respect to charge. And the speed of sound depends on charge through the charge susceptibility. Another thing striking about this expression is that this D is a dissipative parameter, and it's entirely fixed in terms of thermodynamic quantities like susceptibilities, anomalies, the temperature, and so on. This is a kind of surprising aspect of strong hydrodynamic fluctuations. This typically happens that scaling in some sense fixes the dissipation in terms of non-dissipative stuff. So I should say that similar dispersion relations have been observed in the context of 1-dimensional 1 plus 1D hydrodynamics. So there the ballistic mode is coming from momentum conservation, right? It's regular sound. Here, what's kind of cool is that we don't need momentum conservation, right? We got a ballistic mode from the anomaly. So this dispersion relation is going to be robust against disorder. Okay, and this is just how it propagates again. So another consequence of this KPZ scaling in the IR is for transport. And in fact, the KPZ scaling function, so I should say some things about the KPZ fixed point are known exactly, like the dynamic critical exponent. They're fixed by some symmetries if you're clever enough. But some things are not fixed exactly, like the KPZ scaling function. And in fact, correlation functions at the in the IR will be given in terms of some scaling function, which is known numerically to high precision, but there's no analytic expression for it. However, some of its limits are known. And so from this KPZ scaling function, we can get the optical conductivity on the edge, which ends up having this singular 1 over frequency to the 1/3 behavior. And the coefficient is just known is known numerically and involves these factors. Okay, so these are kind of the two main results of this paper with Paulo, this anomalous dispersion of edge modes and singular connectivities on the edge. So now all this has been with a single hydrodynamic mode on the edge. Of course, there's another mode that is natural to take into consideration, heat. Heat is also conserved. It has a slightly less special status than charge on the edge because it's easier for heat to leak out in experiments. But you know, we trust our experimentalist friends. They know how to make good insulators. So let's assume heat is just conserved on the edge. And let's include it now. So let's first include it and completely neglect thermoelectric effects. So if we just have kind of separate, you know, a heat mode and a charge mode, they're just going to do their own things. And the heat mode will also propagate chirally if the bulk has a thermal Hall connectivity. And the conclusion will remain the same. We'll have two decoupled KPZ fronts, okay, that just spread with their own velocities, their own non-universal velocities. And it turns out that this conclusion is actually survives against thermoelectric effects, basically because these two modes, although they're strongly interacting with themselves, they don't really like to interact with each other. It's kind of kinematically disfavored for these two sound modes to interact with each other. So basically, thermal transport is similarly singular and has this weird optical finite frequency behavior. So there's one special case that's a bit different, which is for quantum Hall systems where the thermal Hall connectivity vanishes. So this happens, for example, for the nu equals 2/3 states. And in this case, the heat mode is not ballistic, right? It's just kind of stays in place like this. And the linearized analysis would tell you that it's just simply going to diffuse. Okay, there's no ballistic part. So I told you before that diffusive hydrodynamic excitations always, the interactions are irrelevant. But here there's something a bit special, which is that this heat mode is going to be coupled to a mode that's strongly fluctuating, this KPZ charge mode. And so even though the heat mode doesn't have these relevant self-interactions, because it's not ballistic, it does talk to the charge mode, which is strongly fluctuating. And so you have a kind of a problem of these two coupled equations. And this turns out to be an open problem in stochastic physics to find the critical exponents of this system. It's not known. But there's a completely uncontrolled approximation that gives the following critical exponent, which turns out to be very close to what people observe numerically. So, okay, it might be close to truth. And so what we would find is that this heat mode, instead of spreading diffusively, spreads with this funny power of K. The optical connectivity is still singular, but it has a slightly different power because it talks to this softer heat mode. Okay, so let's see, I still have some time. So I'll talk a little bit about experiments. So our two main predictions are the singular edge transport and anomalous damping of edge modes. It's a little bit difficult, as far as I know, to look at to study optical connectivities of edges. What's usually done is you shine light against the surface, and then you can measure the optical connectivity of the surface. So it might one way could be to look at these chiral surface metals. But this prediction actually seems much more promising to compare with experiments, because these edge modes have been studied a lot already. They've been seen in a number of systems, for example, in gallium arsenide, which is probably the most famous quantum Hall system, but also in graphene, in cold atoms. And so these edge modes have been observed a lot. Their damping hasn't been studied too carefully, although it is known, it is well established that the damping has this linear dependence on filling and a weak temperature dependence. But the wave vector dependence hasn't been studied too carefully. In fact, the only paper we found that studied it gave us a lot of hope because what they found was a magnitude of the damping that increases with a frequency or a wave vector somewhere between linear and quadratic, which is exactly consistent with what we would like. Okay, but this is an old paper, and my experimentalist friends tell me to be careful with these old papers. Techniques have substantially improved, so it would be nice to kind of confirm this behavior in more modern experiments. So there was this interesting case when we have a vanishing thermal Hall connectivity. And what's interesting here is that the heat mode kind of is not ballistic, so it stays in place. And in fact, it spreads on both sides, and it leads to what's called upstream heat transport. So it's a situation where it's easier to measure the heat mode. Of course, it's always harder to measure heat, right, in general, than charge. But here, because it's the only thing going upstream, it's a bit easier to measure. And there's some experiments that have been measuring this heat mode. So there it would be interesting if we could see some of this anomalous behavior in these experiments. In particular, there's something these experiments found was that there's a much stronger finite size effects in this setup for the nu equals 2/3 state than in other states, which might have something to do with the fact that the modes are even softer in this case, as we found here. Okay, so that's basically all I wanted to say for today. Thanks a lot for tuning in, and I'll take questions.
Thanks, Luca. Yeah, I'm sure there will be some questions. So please, whomever wants to ask a question, just unmute themselves and ask.
Hi, Luca. Thanks for the talk. So maybe you can clarify my confusion here about this KPZ edge mode, where the dissipative coefficient is determined by non-dissipative parameters.
Yes.
Like, how does entropy production work here?
Yes. Yeah, it's pretty confusing. But actually, I'm going to turn the question back at you because I learned this from one of your papers. There's another case where this happens, which is a bit less mysterious, which is just hydrodynamics in 2+1 dimensions. So their interactions are marginal, they're marginally irrelevant. So you still have kind of regular hydrodynamics, but as you explain in your lecture notes, there's the hydrodynamic coefficients have some logarithmic running. And in the deep IR, if you just follow the logs all the way, which in practice might never happen in experiments that we go all the way there, but just let's be theorists. In the deep IR, they're entirely fixed in terms of thermodynamic quantities as well, right? So that's just another situation where hydrodynamic fluctuations leads to So yeah, I'm not answering your questions, but this is another situation where it happens when you have this running of transport parameters.
Do you know if there is an easy way to look at the entropy current in this system? I don't know.
Yeah, I think you could probably. I mean, this guy could be the heat mode, right? So you're saying you would probably find some entropy production proportional to this stuff, and you're saying this is a bit weird. So okay, just I think a kind of conceptual answer. I don't know if this will be very satisfying, but in the case where fluctuations are weak, I like to think of dissipative things like diffusion constants as coming from the UV, having integrated out the UV, and they might get corrections, but basically they're coming from the UV stuff. Here, and in this case, you could do some more RG, and you'll get hydrodynamic contributions to these transport parameters. And when hydrodynamic fluctuations are weak, it's usually not very important corrections to these transport parameters. But when they're strong, hydrodynamics itself will give will control dissipation. So I think maybe that's one way of viewing it. Here I started with a diffusive system in the UV in some sense, and I flowed to the IR and found this KPZ stuff. And dissipation in the KPZ is coming from these, UV diffusive modes in some sense. I think you could even make this precise if you had some kind of large N theory where you have a window between which, the diffusive behavior and the KPZ behavior between these two regimes.
Okay, thanks.
Hi, Luca. I have a question about the counting of one-way and correction.
Mm-hmm.
So, like, there was you have an argument about counting the power of k and see which one is relevant. Like, can you have like similar argument for the large N counting? Like just seeing from similar argument that you made at the beginning, or is there a clear way to do that?
Yeah, there's not a scaling argument, but let me just go to where I see. Yeah, there's not really a scaling argument that tells you. Let's look at the diffusive guy. The dependence on N, but it just turns out that let's see if we can see it in some way. Yeah, I mean, it's, charge, okay, here I suppressed, okay, charge hydrodynamic correlation functions are always proportional to, maybe I wrote it in the case of the relativistic fluid, to the number of degrees of freedom. Here you see it for relativistic fluid, there's the entropy density, okay? Mm-hmm. Or even in the diffusive case, there's this susceptibility, which is going to count degrees of freedom. So correlation, and this is kind of the semi-class, this is the thing so this is going to have powers of N. And so these are the powers of N that end up killing you in loops. So they're kind of like a loop counting parameter. So notice that we don't need a loop counting parameter, right? Because when interactions are irrelevant, it's like in a regular effective field theory, the coupling, the natural coupling is, interactions are suppressed by the cutoff in some sense. They're suppressed by the energy scale you're looking at divided by cutoff. But in large N systems, we have an additional loop counting parameter, which comes from the fact that correlation functions are all proportional to the number of degrees of freedom. So here it's going to be N squared.
Okay, thank you.
There's no more questions. Let's see. Well, we can thank you again. Maybe there's, Carlos, please go ahead.
There's just one question. So you talked about charge current and heat current. Have you thought about spin current as well?
Yes. Yeah. Thanks for the question. Yeah. So for example, in the quantum spin Hall effect, you could ask about this. So yeah, this stuff. In fact, all it requires is a chiral edge mode. So, also another example is topological superconductors or quantum spin liquids that are gapped in the bulk and have this. Their charge is not really doing anything interesting, but heat is the main player in the game. And there you would expect a similar situation. And then, as you say, you could have spin, anomaly and flow of spin. And anomalous dynamics of spin on the edge. So yeah, I think a similar conclusion would hold for spin. With some, spin is not going to be allowed to mix with charge, for example, but on its own, it's going to have, I expect it to have some KPZ dynamics as well.
Mm-hmm. Okay. Thanks.
Any other question for Luca? Last chance. Okay. So it looks like there's no more questions. So thanks a lot, Luca, for this very nice talk. And that will be all. Just let me say that next talk is in a week from now, so May 5th, and it will be Eric Mefford from Paris talking about transporting quantum clean superfluids. So see you next Thursday, and thanks again, Luca, very much for your talk.
Thanks.
Bye, everyone.
Bye.
Ciao.